let us see some of the link prediction methods that we generally use. Although the methods that we are going to talk about here, these are generally used as baselines, right, for link predictions, but these are useful to understand. Okay. So, if you look at the taxonomy of link prediction methods, right, you can see that mostly they are divided into these three categories. The first one is heuristic based models, where we essentially take some heuristics about the node attributes and the connection properties, and then based on the heuristics, set of heuristics, we predict whether this link exists or not, right. We will in this lecture we will discuss some heuristics based on local similarity measurement and some metrics based on global similarity measurement. In fact, there are also a few metrics which fall in between. Those are called quasi similar metric, right, quasi local similarity metric. Okay. So, the second category is probabilistic models, where in which we basically try to measure the probability of appearance of a particular edge, right. It can be supervised, it can also be unsupervised. For example, this hierarchical random graph model that we will discuss here, that is more of an unsupervised approach, whereas supervised random walk is a supervised link prediction approach that we will discuss. And we will skip this one. This is more of a information theoretic model, where we look at entropy based models and see whether mutual information based entropy based models can be useful for link prediction tasks. So, let us start with the metrics which are generally used to capture different heuristics. Okay. So, generally the similarity between nodes can be derived using a combinations of different properties. It can be a combination of node level properties, edge level properties, as well as node and edge and metadata in related properties. For example, say node level structural properties include say degree, clustering coefficient, these kind of features, whereas metadata of a node, for example, in case of social network, you can fetch the location information of a user or job or say say gender or some other interest, political inclination and so on. These are basically metadata related properties that we often use. And as I mentioned, we will look at three types of such metrics. One is called local heuristics, the second one is global heuristics, and in between these two we have quasi local, semi local kind of heuristics. Okay. All right. So, local heuristics, let us consider a graph, an undirected graph G, V, comma E, and there are say 3 nodes x, y, z. These 3 nodes belong to V at the current, of course, at the current time instance, and let us assume that x and z are connected, y and z are connected, but x and y are not connected. So, how do we decide that whether x and y will be connected in the future? Okay. So, we will discuss these metrics. We will discuss something called common neighborhood metric, common neighborhood similarity metric, Jaccard coefficient, preferential attachment, Adamic adder, Salton index, Hub promotion index, right, and so on and so forth. So, these are some of the example metrics that we will discuss today. Okay. So, the simplest one is the common neighborhood similarity. It basically says that given 2 nodes x and y which are not connected, let us look at the common neighbors, okay, x's neighbors and y's neighbors, and the more this common neighborhood set, the higher the similarity between x and y. In this case here you see that A and C, they are not connected. So, this broken edge, this does not exist, but A has node F, node B, node D, node E as neighbors, node C has F, E and D as neighbors, Therefore, the intersection of the neighbors of A and C would be 3, the size would be 3, so the similarity would be 3. Okay. So, this is the simplest measurement, and in the matrix formulation, if you think of, if you take adjacency matrix A, essentially you are looking at the second of distance, right. How many such paths are there between A and C of size 2, right. So, this is one path, okay. This is one path and this is one path. So, essentially, and how do we measure the number of paths of size 2, of length 2? We just multiply A with itself, A square. Now, the similarity between x and y is basically the entry of x and y, the xth and yth entry of A square matrix. Okay. So this is common neighborhood. The next one is Jacquard similarity, and so the problem in common neighborhood is that, say for example, A has a lot of neighbors and C has only one neighbor, right. So therefore, automatically when we take the intersection, right, the intersection, and say let's assume that that C's neighbor is also A's neighbor, right. Say this is C and C and say this is A, right. There is one common neighbor, but A has a lot of other neighbors. So automatically, if you take the intersection, it would be 1, right. So you are, but A and C are not similar, right. So but you are not penalizing the fact that A has a lot of degree, right, which lot of neighbors which are not common for C, right. So this matrix should be normalized. Okay. Now Jacquard similarity is basically a normalized common neighborhood similarity in which the numerator is same, basically intersection of two neighbors, and the denominator is the union of two neighbors. Now when we take the union, you basically penalize the fact that a node has a lot of neighbors and the other node has very few neighbors. Okay. Say in this case, if you see, node A has 4 neighbors, right. Node B has 3 neighbors, right. Intersection is 3, union is 4, therefore 0.75. But if you take that example that I have given earlier, this one, say this is C, this is A, and let us say there is a common neighbor x, but A has say 50 other neighbors. Okay. So intersection would be 1 and the union would be what? The size of the union would be 51. So 50 neighbors here and this one 51. Okay, 1 by 51, which is much lesser, right. So this is Jacquard index, and then we say that okay, right, these two nodes are similar, then you basically rank all the node pairs based on Jacquard similarity, and you return top 5 highly similar node pairs, right, and you say that okay, you know, this 5 pairs will be connected, right, in the future. So let us look at some other metrics. So one is called Salton index. Okay, what is Salton index? Salton index is, so Salton index between x and y is neighbors of x, right, intersection neighbor of y, okay, and you take the cardinality of this and square root of kx, k sub x and k sub y. K sub x is the degree of x and k sub y is the degree of y. This is again another way of normalizing the common neighborhood, right. So numerator is same as the Jacquard coefficient, right. The denominator is different. Here the denominator is essentially the degree, right. You are also considering, so in case of Jacquard coefficient, the denominator was the size of the union, right? And when you take the union, you basically do not duplicate, do not count the common neighbors 2 times, okay. Common neighbors are counted 1 times, right? But if you take the degree, common neighbors are also counted 2 times. So in order to reduce the effect, because it may happen that there are many common neighbors and you are counting this common neighbors double times, right? So you take the square root, so the effect will reduce, okay. So this is Salton index. Similarly, there is another matrix. Now these are, look, so I mean you can also come up with your own way. You can say that, look, I will not take square root, I will take 1 by 3, okay, or 1 by 4, does not matter, right? It depends on the application, and depending on the application, you can think of your own ways. So the other one is called Sorensen index, okay. Now these names are coming from the inventor of this matrix, okay. So this is SXY is 2 times intersection of this one, okay. Essentially you are taking the intersection and then you are normalizing it by the average degree of x and y, x plus y by 2, right. This is called Sorensen index, okay. So now let us look at another interesting metric called Hub depressed index, okay, HDI. So this HDI between x and y is neighborhood of x intersection neighborhood of y. You see that this numerator is common, almost same, right, for all the cases, only the denominator changes. And then you have max. Here we were not taking the average, here we are taking the max. So this is called Hub depressed index. And similarly, there is another metric called, let me write these 2 metrics side by side, Hub promotion index, Hub promoted index, okay, HPI. So S of HPI xy is intersection of neighbors of x and y divided by mean of kx and ky. What does it mean? Okay, what does it mean? So, okay, so let us look at this denominators carefully, okay. So this is called Hub promoted index, meaning that if x is connected to a node y, which is a hub, so hub will promote you, okay. So let us say, sorry, I mean x and y are not connected, not connected, okay. So you are trying to understand whether x and y will be connected or not. So if x is a x, I mean if we are measuring, right, the similarity between x and y, and one of them is hub. So if one of them is hub, then its degree would be huge, right. Say y is hub, so x y would be much greater than x of x, because it is a k of x, right, because it is a hub. So therefore when you take the minimum of this, always the other node which is not hub, that will be considered here in the denominator. So in other ways, hub basically promotes the other node to use its own degree. So you will basically be better off if you are surrounded by hubs. Similarly, this is the other one is called hub depressed, because we are taking max, right. So if you are surrounded by hubs, the hub's degree will be dominated. So the hub's degree will dominate this metric, right, and because you are taking max, so k of y will be considered here, right. So, this would be high, okay. Your degree would not play any role. So, now these are some of the metrics which we use in not only link prediction but also for in general similarity measurement, okay. So, the next one is called preferential attachment. Now, preferential attachment is something that we already discussed in the network growth model chapter, right. So, here the idea is that the philosophy behind preferential attachment is that two nodes are connected due to a node will get connected to a node based on its degree, right. So, it is highly likely that the degree, both the degree would play an important role, right. So, likelihood of a node x to obtain a new edge is proportional to kx. This is called preferential attachment. Therefore, the preferential attachment score between two randomly selected nodes x and y is just the multiplication of their degrees, kx times ky, okay. So, this is the very simple idea, and this kind of metrics, this has a lot of applications in different to quantify different functional significance of links subject to various, say, node based dynamics such as percolation, right, propagation, synchronization, transportation, and so on and so forth. So, now let us look at a very important metric, okay. But before that, let me discuss another metric which people generally use. Light-Holm-Newman index, right, LHN, okay. This is kind of similar, intersection of the neighbors, but the denominator is kx times ky. We have taken, we have seen average, max, mean, now multiplication, okay. All right. So, now let us look at a very important metric, right. Now, this has been used as a baseline for quite some time, although it was proposed long time back. This is called Adamic adder distance or Adamic adder similarity, right. And two researchers, Lada Adamic and Adder, so they proposed this metric. So, Adamic adder distance between two nodes x and y is sum over, we look at the common neighbors, okay. You see here gamma x intersection gamma y, right, common neighbors, and z is one such common neighbor, and we take 1 by log of kz. What is the intuition behind this, okay? Let us try to understand. So, let us say A and B, okay, and they have common friends, two common neighbors C and D. So, C, you see that C has a lot of degree, all right. C is connected to many nodes, whereas D is connected to only A and B, okay. It means that D is more dedicated to A and B compared to C. So, any information, if it comes to C, right, if it comes to C, the likelihood that C will pass that information to B, say, right, say an information moves from A to C, the likelihood that C will pass the information to B is lower than the same for D, okay. So, we basically penalize those nodes, those common neighbors which have a high degree, okay. In this particular case, you see C will be penalized because C is not dedicated to A and B, whereas D is dedicated, okay. So, the metric basically says that we take the sum the intersection of the neighbors of x and y, and z is one such common neighbor, we take 1 by kz. Kz is the degree of z. So, higher the degree, lower the importance, because we take 1 by x, kz, right. Of course, we can take log because we want to dampen the effect, so we take the log. Okay. In fact, there is another metric called resource allocation index, same as atomic adder, but here they do not take the logarithm of the degree, they just take the degree. Okay. Now, this is a very interesting idea. Okay. You are basically saying that it is good to be connected with less nodes, to be connected with less number of nodes which are common neighbors, which have less degree compared to the case where you are connected to a lot of nodes, but the common neighbors have higher degree. Okay. So, Salton index, half promotion, half depressed we already discussed. Let us look at the global heuristics. So, these are local heuristics, the metric that we have discussed so far. In the local heuristics, we only look at the neighbors, and based on that we judge, right. Now, global heuristics with respect to the entire graph. Okay. The first one is cart centrality, cart score, right, and this cart score is motivated by the cart centrality that we discussed earlier. Okay. So, the cart score between x and y is forget about this part, right, is the number of paths of length p. Okay. And we take all paths, all possible paths of all possible lengths. Say you have length 1, length 2, length 3, length 4, length 5, right, and between x and y there are 2 paths of length 1, 3 paths of length 2. Remember, there can be multiple shortest paths between a pair of nodes. Okay. So, you have 2 shortest paths of length 1. I mean, of course, let us not use the term shortest path here. You have 2 paths of length 1, 3 paths of length 2, 1 path of length 3, 2 paths of length 4, and 2 paths of length 5. Okay. We basically sum them up. Okay. But we also penalize the paths having higher length, okay, which is controlled by alpha. Say alpha is say alpha is 0.5. So, you penalize this in this way. So, the contribution of this part would be 0.5 to the power 1 times 2 plus this would be 0.5 to the power 2 times 3. Now, this 1 is the length, 2 is the length, this would be, so plus 0.5 to the power 3 times 1, this would be 0.5 to the power 4 times 2, and this would be 0.5 to the power 5 into 2, right. So, as you move further, right, you see the contribution will also decrease. So, this is 0.5 times 2, this is 0.25 times 3, this is 0.125 times 3. So, although you may have more number of shortest path, more number of paths, say 3, 2, whatever, but the contribution will decrease, because now you multiply it by 0.25, then 0.125 and so on. This is exactly same as the cart centrality that we discussed, but here we take the pair of nodes, right, and this alpha is a damping factor, same as the cart centrality. Okay. The next one is called heating time. What is heating time? So, heating time, before understanding this again is based on this random surfing behavior, right, random walk process. So, you start your random surfing from a node x, right, you basically move to a neighbor of x, again you just choose one of the neighbors uniformly at random, and then you move there, again from that node you choose another node uniformly at random, again the neighbors, one of the neighbors, and then you move there. So heating time between x and y is the expected number of steps a random walker needs for to move from x to y. So why do I say that expected number of steps? Because this is a random walk process, and depending upon your trials the path length will change, right. So you basically repeat these experiments again and again, and you take the expectation of this, and that would be your heating time. And we take the negative minus y because we want that higher the heating time, so lower the heating time, better would be, right. Better would be the similarity, or higher would be the similarity. So lower the heating time, higher the similarity between x and y. Therefore, you take the minus, because if we take the minus, then higher then we can say that higher the negative of heating time, higher the similarity, right. So higher the better. So in order to satisfy this, we basically do this thing. So sometimes what happens is that this measurement, that the heating time, this is not normalized. Okay, if this is not normalized, what I mean, you basically want to make this thing between 0 to 1. So what you do, you multiply this with the stationary distribution that we obtained from the page rank. Hope you remember what is page rank. You basically repeat, because page rank always guarantees that this would be the stationary distribution. In the stationary distribution, the sum would be 1 and each would be between 0 to 1. So you basically multiply this quantity with the stationary distribution of the value of x from the stationary distribution of the page rank process. Okay. The next one is commute time. So here the idea is same, but here we look at both the things. So in the heating time, we start from x and see when the random walker will hit y, right. Here you start from x and you measure the heating time to reach y. You also start from y and you measure the heating time to reach x, right. So htxy, htyx, you take the sum and that is your commute time, okay, and of course you take the negative, the same, due to the same reason. And if you want to make it normalized, you multiply it by the stationary distribution of x and y in the page rank process. Okay, so this is pretty much about the local heuristics that we use, local and global heuristics that we use for link prediction. Okay, for essentially for measuring the similarity between two nodes. But if you remember in the link analysis chapter, we also discussed measures like sim rank, path sim, right. So sim rank, path sim, those are also used for measuring the similarity between two nodes, right. Sim rank was in sim rank, if you remember, it was basically based on the idea that how similar the neighbors of your nodes of the given pair of nodes, right. In case of path sim, we look at the heterogeneous graph, and then we look at the meta path, and we look at number of meta paths of certain types, and so on and so forth. So those metrics can also be used for link prediction. Okay, so we stop here. We will discuss this algorithm in the next lecture. Okay, thank you.